So on your handout, you have all of these problems, beginning with this one here. Find the ratio of speeds of an electron and a negative hydrogen ion accelerated through the same voltage, assuming non-relativistic final speeds, meaning we don't have to use the Lorentz contraction factor, which is 1 over the square root of 1 minus v squared per c squared. But anyways, so let's get at it here. So basically, hopefully you remember from a previous installment of this show that the kinetic energy, okay, will end up equaling charge times voltage, the big V for voltage. So that means that, for instance, for the electron, all right, so if this is going to be the kinetic energy of the electron, we're going to have 1/2 the mass of the electron times the speed of the electron squared will equal QV. And for the kinetic energy of the hydrogen ion, that's also going to equal QV. And so we'll have 1/2 mass of the hydrogen ion, velocity of that hydrogen ion squared equals QV. Well, basically, the ratio ME to V squared and the hydrogen, that just equals 1. If you, since we're talking about ratios, so hopefully you can see that the halves drop out. The QV over QV is 1. They each are equal to that. And so this means that our ratio of electron speed to the hydrogen speed is just going to be the square root, and everything gets flipped over. All right, so it's going to be that ratio is going to get, it all washes out, just a number, that's all we're looking for. And so the mass of a hydrogen ion, well, let's see, oh, it's given. I knew it did that for a reason. And 6/7 times 10 to the minus 27th. And then a electron is 9.11 times 10 to the minus 31 kilograms. And that ratio is 42.8. So just ratio of speeds, but we don't know the speeds, but we would know the kinetic energy associated with its charge going through a potential difference. That's the idea. And so, you know, it's not like we have a radar gun for electrons and hydrogen ions, okay? We sort of do, but we work it backwards from the energy. And the energy can be defined in terms of things that you do know, namely the charge and the potential field that it went through. So that's the idea. And so you use a basic idea, fundamental idea rather, of physics, energy, kinetic energy, and its association with charge and potential. All right? So we get a ratio, and the main point of this problem isn't so much to get the ratio, but it is to get the connection between kinetic energy and potential fields. That's the key element, and the ratio just gives us a way to pay attention to it. Number 2, an evacuated tube uses an accelerating voltage of 40 kilovolts, 40,000 volts, to accelerate electrons to hit a copper plate and produce X-rays. X-ray machine. Non-relativistically, again, not worrying about the factor, what would be the maximum speed of those electrons? And one more time, it is the case that 1/2 mv squared will equal charge times the potential difference, or the voltage. And that means that V, it's going to be the square root of something. Double the other side, divide by the mass. And let's see here. We'll get the square root of 2 times electrons, so it's 1.6 times 10 to the minus 19 coulombs. The voltage was 40,000. The mass, again, of an electron, 10 to the minus 31. So our speed ends up being 1.17 times 10 to the 8th meters per second. So this is getting pretty close to the speed of light. 3 times 10 to the 8th is the speed of light, 300 million meters per second. So we're getting there, all right? On our way. Basic problem. Number 3. A bare helium nucleus has 2, I don't know what an unbare nucleus is, but I guess it's just a plain old helium nucleus, has 2 positive charges, massive, that number that we used the other day in another problem. Let's calculate its kinetic energy in joules at 2% of the speed of light, and then convert it to electron volts, and what energy we would need to obtain that. All right, so part A. Kinetic energy, you know it's half mv squared, so we're going to get 1/2 mass of the helium, and then we at 2% of the speed of light, so that means 0.02 times 3 times 10 to the 8 meters per second. That gets squared. So that 2% of the speed of light squared, but 2% of speed of light and all of that squared. So the kinetic energy will end up being 1.2 times 10 to the minus 13 joules, which is a lot for a little thing like a helium atom, nucleus, rather. So there we have it. It's energy at 2% of speed of light. What is this in electron volts? So an electron volt, there is 1 electron volt per 1.6 times 10 to the minus 19 joules. So it's a definition that I put into a fancy form of 1. 1 electron volt equals 1.6 times 10 to the minus 19 joules. Now you might recognize 1.6 times 10 to the minus 19th is a fundamental unit of charge. Okay? So it's the energy associated with 1 electron. Okay? And so we can just literally convert 1.2 times 10 to the minus 13 joules, multiply it by that conversion factor, and we'll get electron volts of 7.47 times 10 to the 5th electron volts. Now, I think I meant to define electron volts the other day. I can't remember if I did or not. You might recall from the movie, Einstein's big idea towards the end there, Meitner, is it Meitner or Meisner? Meitner. The gal, the Jewish gal that got gypped out of her Nobel. Lisa Meitner, I think it is. She did that packing fraction thing, and there's 200 missing mega electron volts, and that was a confirmation of Einstein's theory. And so electron volts are the kind of thing that a particle physicist or whatnot would use in that sort of work. All right, C. What would be needed to obtain this energy? And so, again, kinetic energy is charge times voltage. So what voltage would be needed? So my voltage is going to be kinetic energy per charge. So I'm going to go back to that 1.2 times 10 to the minus 13 joules. And then there's 2 of those fundamental units of charge in our thing there. And so joules per coulomb is what a volt is, and we get 3.7 times 10 to the 5th volts. So that's it's a lot of volts. That's 370,000 volts, 370 kilovolts. Right? So what does that compare to? The big power lines, the huge steel ones, those are 500,000 to 1 million plus volts as they run across the country. Basically, you need a really high hill to dump all of that electric water down, so to speak. And so you need huge voltages to push it long distances, and then it steps down at substations and whatnot to get down to your house, et cetera, et cetera. All right? So lots of energy put into getting these things going. This is the kind of energy that's on par with power delivery on a national power grid to get particles like this and experiments going places. All right. And again, these problems, it's just what would you use this sort of stuff for? And as future scientists and engineers, inevitably, you're going to be in the kinds of places where these sorts of questions are being asked. You need to reconfigure the X-ray machine. You're working in a national lab. You're building a pieces part for a national lab or et cetera like that. And so you need to know these things that show up in a physics course. All right? All right, number 4. Singly charged gas ions are accelerated from rest through a voltage of 13 volts. So let me pause here. Charged ions accelerated through a voltage. That should get you thinking, K equals QV. All right? The energy, work done, etc., is QV. Charge times voltage, the potential difference. All right? Not to be confused with the little v in speed. What temperature will the average kinetic energy of gas molecules be the same as that given these ions? All right. In this case, it's been a while since we did ideal gas law. We did just a day on it in first semester. You saw it at least once in chemistry. And so this kinetic energy with respect to gases, 3/2 little k T. The little k here has nothing to do with Coulomb, okay? And the T is for temperature in Kelvin, all right? Well, it's this 3/2 kT version of kinetic energy that's going to be equal to our QV. So that's a new thing. You might want to just pause for a minute and note that this is the kinetic energy of gas molecules. That's what this is. All right? And that would be something you would have seen no sooner than last semester, most likely, and then possibly in your chemistry course. Okay, so kinetic energy fundamentally is 1/2 mv squared, but depending on context, you might have a slightly different tweak on that. And this would be one of those times. So I wanted to let that out of the bag. And so what temperature will this happen? So this right here, so I will be able to develop the equation that the temperature will be 2/3 QV over K, which I believe that K is the Boltzmann constant. Okay. We ended up your ideal gas law typically uses the Rydberg constant, big R. That's the NR in the PV equals nRT, but you could write PV equals KT or NKT rather. But anyways, we have this. So 2/3 times the charge, which it's just individual ions, so 1 times 10 to the minus 19 coulombs. Voltage 13, just 13 volts. Yes, just 13 volts. And the Boltzmann constant is 1.38 times 10 to the minus 23 joules per coulomb. So notice that 13 volts over some number of joules per coulomb, that's just a 1, all right? Anyways, here's our temperature. I'm sorry, not joules per coulomb. That's joules per Kelvin. That was 13 volts. All right. The volts is going to be joules per coulomb. That'll kill the coulombs. So just to be clear here, this volt times that coulomb, since a volt is a joule per coulomb, gives you joules. And then that joules over this joules is no joules, and that K comes up to the top. Hence you get Kelvin. All right, so just a little unit analysis, just to be clear. And so all of that works out to a whopping 10 to the 5th Kelvin, which is kind of large temperature. You convert it back to Fahrenheit or Celsius, so that's a lot of energy associated with accelerating those things. Are probably making some plasma or something. And so that's it. We got our temperature associated with that. So why would that matter? Well, if you're building the contraption or building the control system for that contraption, which would involve the sensing and set point violations and alarms and the code, or the materials that hold it all together, got to take whatever temperatures, et cetera, et cetera. How are you going to power the thing up? Well, you only need 13 volts, so that shouldn't be too hard. All right? So these are simple problems for very complicated applications. And that's the end goal for you as scientists and engineers, is to recognize, yeah, while the thing we're working on is complicated, the underlying physics typically isn't. All right? So, but unfortunately, your real job will not come with a workbook and a student answer manual, right? You'll have to rebuild it all. All right, number 5. Temperature near the center of the sun is thought to be 15 million degrees Celsius. By the way, the sun keeps giving us surprises. It doesn't always do things that we think it should, but it's not like we have a lot of places on Earth where we can test such a wild configuration of such huge amounts of hydrogen and electric and magnetic fields. And so we get weird things, and our theory is generally correct, but it has anomalies that we often don't expect. But anyways, surface is hotter than the middle, weird stuff like that. Temperature near the center is 15 million degrees Celsius. Through what voltage must a singly charged ion be accelerated to have the same energy as the average kinetic energy of ions at that temperature? Okay, same thing as before. 3 halves KT equals QV, which means our voltage would just be 3 kT over 2Q. So our voltage, 3 times, what is it, 1.38, 10 to the minus 23 joules per Kelvin, times 15 million Kelvin. I'm sorry. Yeah, close enough. And 2Q, 1.6 times 10 to the minus 19 coulomb. So our voltage going to be 1.9 times 10 to the 3 volts. So almost 2,000 volts. That's not incomprehensible. You can go to a substation anywhere in town and find voltages of that level. Problem solved. Continuing here. What's the average power output of a heart defibrillator that dissipates 400 joules of energy in 10 milliseconds? Now this is an easy problem, but I put it in here because some engineer made these portable defibrillators, or makes defibrillators. Probably a lot of companies that make defibrillators, a dozen or so, I imagine. It means you got engineers on staff, and that means those engineers have to not only get it right, but they just can't have any old defibrillator. You know, you can have a defibrillator that wakes you up for a second, and then you're dead, okay, because it zapped you. And so obviously you don't want to kill people, but engineers have a code of ethics, and you're not excused from any shortcomings in your understanding of things. You're expected to know what you're doing. And so there really wouldn't be any excuse if you screwed that up. Sort of like, think back to the Space Shuttle Challenger disaster. They should have known better. And the two engineers did know better, and they wrote a letter and they washed their hands and said, it's on you. We told you not to do it. But the management didn't want to upset photo op for the vice president, so they did it anyways. All right. Anyways, so you have not just getting paid to have a functioning product, but there's an ethics thing. You need to make sure that this really does work and doesn't screw people up. All right. It's supposed to save lives, not end lives. All right. So here we go. Power. Let's just be clear about this. Average power output, well, power is always work per unit time. That is the definition of power. And if it dissipates 400 joules of energy in 10 milliseconds, well, that's the work. Dissipating energy means work. Transferring energy is a better way, and 10 milliseconds, so 10 times 10 to the minus 3 seconds. And so this is pretty simple. 4 times 10 to the 4th watts, which would be, what, 40 kilowatts. So on this level, this is just the power requirements for the device. And so whether it's plugged in, which means there has to be some sort of transformer, whatever, circuitry or block or something like that for the one that stays in the hospital, to the one that's charged up and goes with the paramedics, to the one that might be stuck on the wall somewhere in a building. You've probably seen those in places. Maybe those are at 40 kilowatts or something else. But so just this is a design element. How do I power the dang thing? Because somebody already knows 400 joules is what you need to deliver in this time frame. So you go into this knowing what the power, the constraints are. You want to make sure you read that right and not think it's 4,000 joules in 10 milliseconds, all right? Or 4,000 joules in 10 seconds, right? That would, we need a little bit longer than, or shorter time than 10 whole seconds in millis. All right, so that's part A of the problem. We got our 40 kilowatts out of that. Part B, so considering the high power output, why doesn't the defibrillator produce serious burns? Well, it's not like there's a formula for this, so I'm just going to tell you. It does not create burns. I have to change my typing to a different color. There it was in white, which would be hard to see on a white background. Sorry about that. It does not create burns because the skin conducts electricity pretty well at high voltage. All right? Such as the ones used in a defibrillator. The gel, has anybody ever seen or done or been defibrillated? You know, you watch it on the shows or the movies, they gel up the pads, you know? Okay, and so that gel just sort of aids in the energy transfer, all right, to the body so that the skin doesn't absorb all that energy. So that it will pass on through to the heart. All right, so you can imagine you're hoping that in the testing of defibrillators, nobody really got burned, all right? But maybe they did. Maybe that's where the gel came into play. But you would think that maybe they would know in advance. You know, if you deliver much more power than this electrically to a human body, you're going to end things even quicker than they're about to be. All right, and then you got to say, well, the skin can the skin handle that, or the tissues handle that? And so you go through these sorts of design iterations based on limitations like what you can compute in the thing above. All right? So, you know, if you got burned too bad, you know, you saved your life, but there goes your swimsuit modeling career, you know, because you have these paddle marks on your chest forever. All right. Lightning. Lightning bolt strikes a tree, moving 20 coulombs of charge. That's a lot of charge. 20 coulombs. When one electron is just 2 times 10 to the minus 19th of a coulomb, that's a lot. Through a potential difference of 100 megavolts. What energy was dissipated? All right, let's just start at the beginning here. So your energy, all right, this is going to be the change in potential energy. Which is going to be QV. And so we can just write 20 coulombs times 100 million volts. And so we get this really simple calculation. So 2 gigajoules. 2 times 10 to the 9th joules. B, what mass of water could be raised from 15 degrees Celsius to the boiling point and then boiled by this energy? okay? You need to know this fact that has been obscured from your understanding because thermodynamics is something you study in the next physics course. But it's a relatively simple formula. And you'll recognize, hopefully you recognize the latent heat of vaporization, that L sub V. Did you guys do it in chemistry? Doesn't that show up in chemistry? Latent heat of vaporization, all that jazz? Not yet? Okay. I thought that was a common thing. Well, anyways, M is for mass. C is a specific heat capacity. The capacity of things like water has a heat capacity, air has a heat capacity, everything has a heat capacity. How much energy, heat energy can it take in? And so this sort of just have to press the I believe button. And so the mass of water that you would get would be the total charge divided by these things that are associated with the heat capacity for a particular temperature change and the latent heat of vaporization, which is also associated with a temperature change. There's any material can absorb so much heat and then it changes phase. So that's the short, oversimplified version of latent heat of vaporization. All right? And so the mass will just, where'd my numbers go? All right, so 2 times 10 to the 9th. Oh, by the way, that Q isn't charge. I think I said charge. Q is total heat energy. So let's be careful here. One of the reasons picking this problem set, besides just wide exposure to the kinds of things that can be done with the topic we're studying, is its connection to other topics. And as you might have noticed already in physics, we reuse letters. All right, and so Q has been used so far up until today strictly for charge. We haven't used Q for anything else in physics, as I recall. However, many of you will take a third, maybe fourth semester in physics, and that third semester is a thermodynamics course. And you're going to have big Q all over the place, and it will rarely have anything to do with charge. So the context of MC delta T, that tells you we're dealing with heat energy, which is used the letter Q. Sorry, just work here. So you need to know. Anybody know whether or not they have to take the thermo course for their trajectory? A few of you, okay. It's not all engineers, but it ought to be. All right. So we have that in the top. Then we have 4186 joules per kilogram degree Celsius. So we use C for Celsius and C for coulombs. So times the 85 degrees Celsius, because that's the change in temperature, going from 15 to 100 Celsius, that's the boiling point, all right? Plus the latent heat of vaporization, which is something you would look up in a table, which is, for water, 2256 joules per kilogram. So thankfully those are common units in the denominator. And joules per kilogram, all of this works out to 766 kilograms of water. Okay? So I'm a 200-something pound person, about 100 kilograms. Actually, 95 or something like that. 100's close enough. So almost 7.5 of my mass. So probably, depending on the person in the room, somewhere between 6 and 8 of your body weight in water. That'd be a lot of water. All right. Part C. So, discuss the damage that would be caused to the tree by the expansion of the boiling steam. Well, it would basically blow it up. Okay. Kaboom. Tree gone. Shredded. Vaporized. Partially. Blown to bits. You can't... anybody ever seen a tree hit by lightning? For real? It blows some part of it off. If not, obliterates the tree. So it just varies the size of the tree, et cetera, et cetera. But, you know, it's not like trees typically don't survive being struck by lightning, right? They do, some of them do, but typically it's wreaks a little havoc on them. And trees have a lot of water in them, okay, which conducts electricity. All right, getting in the home stretch here. 12-volt battery-operated bottle warmer heats 50 grams of glass, 250 grams of baby formula, and I left a number out. You know, there has to be a typo. There absolutely has to be a typo. Does yours have the typo in it, though? 200 grams of aluminum?
Yeah.
So the typo is not in your paper, but in mine, correct?
Yeah.
You have the 200 grams there. All right, good. So not a total loss. All right. From 20 Celsius to 90 Celsius, how much charge is moved by the battery? All right. So we have another one of these Q in terms of heat energy. All right, and so we have Q is defined as MC delta T. Okay, but I have multiple masses, and each one of those materials has a different heat capacity, all going through the same delta T, change in temperature. So for us, this means the Q that we're dealing with is going to have an M1C1 plus M2C2 plus M3C3, because there were 3 materials and 3 masses of those materials going through it. And so this equation, Q equals MC delta T, if there's only one mass and heat capacity, then it's easy. But if you have several layers, then you account for all the variations within the system. And so that's how we do it. And this needs to equal, this is heat energy, and it needs to equal the charge voltage, or the potential energy. Energy equals energy. So let's be clear. Energy. So today we've seen multiple forms. We've seen 2 kinds of kinetic equal to QV, and now we have a heat energy that's equal to QV, because energy is energy. That's the beauty of energy calculations. If you can describe the system in terms of its energy, then this energy has to equal whatever equivalent energy is involved with your system. And then it's just math after that. All right. So we were looking for how much charge is moved by the battery. All right. So little q, what we want over there on the right, is going to have our M1C1 plus M2C2 plus M3C3 delta T, whoops, not not that T, over the voltage. Now, we would have, let's see here. Yeah, I can squeeze it in there. So M1, C1. So there was 50 grams, which is going to be 0.05 kilograms for that what is it, the glass part of the bottle. And glass has an 840 joules per kilogram degrees Celsius heat capacity, plus 0.2 kilograms for the formula. Yep. And that has, apparently, somebody knows the heat capacity of baby formula. All right. Not one of those things you pick up every day. Is that the same as water? Oh, yeah. I guess it is water. Didn't recognize it. And then, oh, I left the aluminum part out of the calculation. All right. There's something in there, but I left it out. Oh, no, I didn't. I just not reading my own writing. So 0.25 for the aluminum, and that one, aluminum is 4186. And then all of that, that'll be times the 70. I'm running out of room on my screen here, so yeah.
I don't think we really have 0.2 kilograms.
Is it? Oh, the aluminum was 900 though. I swapped them. So this one is the aluminum. This one is the baby formula. That because 4186 is the one for water. So I had them backwards because I was reading them from the problem instead of my notes. So there should be a times 70 degrees Celsius out there on the right. My toolbar is in the way of writing it. So make sure that that up here you put a 70 degrees Celsius factor. Up there, okay? Otherwise you'll have the right answer for the wrong reason. So the amount of charge required to do that, 7.4 times 10 to the third coulombs, so 7,400 coulombs of charge, which is a lot. 1 coulomb of charge delivered to you in 1 second is an amp, and it will kill you. All right. So that's how much charge has to move. And this will be a little bit clearer when we get into circuits, because that's what current is, moving charge, some number of coulombs per second. Yeah, how many, part B, how many electrons per second flow if it takes 5 minutes to warm the formula? Okay. So if N is the number of electrons, okay, per unit time, okay, so T will be that time. Then we have the total charge that we just calculated. And if I want to count the number of electrons, it's that charge divided by the fundamental charge on an electron, or little e, all right? And per unit time. So basically this will give us 7.4 times 10 to the third divided by 1.6 times 10 to the minus 19 over 5 minutes, so that's going to be 300 seconds. And in the end, 1.54 times 10 to the 20th electrons. Realize that if it was 10 to the 22 electrons, that would be on par with the number of stars in the visible universe. So we have 100 times less electrons in the situation than the observable stars in the universe. So 10 to the 11 would be a typical number of stars in a galaxy. All right? And so 100 million galaxies with 100, yeah, so that's a lot. And that's just in the material, you know, copper wire, parts of the circuit, whatnot. All right, last two problems. Battery operated car uses a 12-volt system. Aren't most batteries 12 volt? Or 12 amps?
Our batteries are 12 volt usually.
12 volt?
There's a couple of 6, still not.
There are, okay. Find the charge the batteries must be able to move in order to accelerate the 750 kilogram car, it's a little car, from rest to 25 meters per second. Make it climb a hill, and then go 25 meters a second under that force for an hour. Okay, there's a lot going on there. So, total energy would equal, there's an energy associated with the speed, there's an energy associated with its potential due to height, and there's an energy associated with the work done to produce a displacement going in. And then you have some stuff going out. Now that FVT, that's power times time, because if you think about it, V is D per T, okay? So FD per T times T is just FD, but it's one of the power formulas, okay? And so we're talking about those sorts of things. So, what do we have going on here? So, at the beginning, we're going to total energy here. We have, let's see, so let's plug and chug. So we have half of the mass of the car, 750 kilograms. The speed was 25 meters per second squared. That going into it. We had changing the height of the car. And the height was 200 meters, yes. And then the force, 500 Newton force at that 25 meters per second for an hour, which should be 3,600 seconds. .60 minutes times 60 seconds per minute. All right, it's got to be So these are all getting the right units. I think everything came in the right units except for the hour. Hour need to be in the seconds. All right. So this is our total energy. All right. And that will give us a total energy of 4.67 times 10 to the 7th joules. And that total energy needs to equal QV. This is a battery-operated car. So the energy, this is tying together 2 semesters now. All that energy calculation to begin with was first semester physics. Forces producing displacements which require time and therefore speed. So kinetic energy, gravitational potential energy, and power dissipation associated with motion, all right, under a force. So 3 versions of energy, mechanical energy, into our total calculation, and that total energy has to be supplied by the battery, which is why energy total has to equal QV, which is electric potential, electrons, all right, stored up and moving, or providing the reason that things move. And what were we looking for? The charge. So this means that our charge will equal the total energy per the potential difference. So we have 4.67 10�7th joules. The voltage was 12 volts. So we need 3.89 times 10 to the 6 coulombs. We need 3.9 million coulombs of charge. So imagine if you could release all of that Coulomb energy in one instance. So to give you an example, you guys know that I worked on a nuclear submarine operating the nuclear power plant. We had a battery. In addition to the nuclear power plant, we had emergency power in 2 forms. We had a diesel engine that we could run, provided we were close enough to the surface. We have a snorkel, this tube we stick up to get air. And then we have a battery. So that battery would, let you go, 4 or 5 knots, okay? And we would constantly charge that battery, and that battery had enough energy stored in it that if we were to release it all at once underneath the submarine pointed up like a rocket, if I remember right, we could get it into space. So this is a 400 and something foot long, 30+ foot wide hunk of steel that holds 150 people and all the toys that go with being on a nuclear missile submarine. All right, so that's a lot of energy. Okay, but it wouldn't take us very far underwater. All right, we could putz around on the surface for a long time, but we would run out of energy relatively fast. If I tell you any more, I have to kill you. All right. Number 10, and I like you. Don't want to kill anybody anyways. All right. Fusion. The probability is greatly enhanced, appropriate nuclei brought together, but repulsion has to be overcome, so there's a strong nuclear force in the way. And so the kinetic energy of high temperature gas, so we have all sorts of fusion experiments happening today. We got lasers that, we have thousands of lasers pointing all around from a spherical geometry onto a little bead inside of a vacuum chamber, or all sorts of things we're working on to get fusion going. All right. So calculate the potential energy of 2 singly charged nuclei separated by 10 to the minus 12 meters. So this is the kind of thing that, particle physicists working on the problem of fusion, and therefore the engineers that work for them, who make the toys and the control systems, write the code, got to know about some of this stuff. All right? So one way or another, you're going to learn about it. So We were told just the other day by our friendly neighborhood physics professor that voltage, potential difference associated with a charge, would come in that form, work done per unit charge. And so this means that QV equals the KQ. Let me write this differently. This means that our potential energy would equal KQ squared per R. All right? So running those numbers, 9 times 10 to the 9th for the K value, 1.6 times 10 to the minus 19 squared for the charge, and the distance was 10 to the minus 12 meters. And so that energy, all that crunches out 10 to the minus 16 joules. 2.304 to be exact. And then part B, these are gas, again, this is gas ions. So our average kinetic energy, that's what the bar refers to, is that 3/2 kT per temperature. So the temperature, part B, what temperature will atoms of a gas have that average kinetic energy equal to that potential? So we're going to have 2/3, flipping that 3/2 over. And then we're going to have for our energy, KE on top will be equal to the QV, or this 2.304 times 10 to the minus 16. And then, what is it? The Boltzmann constant in the bottom will be 1.38 times 10 to the minus 23rd joules per Kelvin. That way we get Kelvin out of this, and we get 1.11 times 10 to the dang Kelvin. All right, 10 to the 7th Kelvin. So fusion's a big deal, pretty big deal to get those things going, but they're working on it, and I imagine they'll figure it out before too long.